Dear students, so welcome to this new video lecture of wireless communication. So today we will start a new topic, fourth generation systems and long-term evolution. So this is basically the 4G LTE systems that you use for your cellular phones these days. So the fifth generation or 5G is also knocking at the door, and at some parts of the world, including China where you all are, 5G systems are already there. So currently this 4G, LTE and 5G are coexisting, and most of the features of 4G in terms of the standards and the protocols are acquired in 5G with some new technological advancements. Okay, so it's worthwhile to study 4G, and then you can appreciate more the concepts of 5G. So in this module, probably we don't have enough time to cover 5G, so I thought I will talk a little bit about 5G, but I don't think I will get that time. But some of the concepts that we have covered so far, for example MIMO, etc., and what we will also cover in this lecture and the next lecture on 4G, you will get to know about some concepts which are also there in 5G, as I said. And then since you are doing the class project, so you already have a lot of topics on 5G, so you will obviously learn something about 5G. And if you are still interested, then I can share some reference material with you on 5G. But right now, let's first start with 4G, and let's see where we go. Okay, so so this picture says that as we moved forward with the generations of mobile communication, we basically we were striving for speed. So the need for speed was there always, and whatever enhancements in terms of technology that happened from 1G to 2G, 2G to 3G, it was basically the enhancements in the bandwidth and the speed with which we can exchange data. So the first generation or 1G, they basically just supported voice services, and it was analog based. Okay, this we have said many times throughout this module. Then the second generation, this was also designed for voice, but the first digital standards came up in the second generation. So GSM, CDMA, etc. So from analog to digital, so there was a big leap from 1G to 2G. And also, as you can see, there was improved coverage and capacity. So the speed was enhanced from 2.4 kbps to 64 kbps. Okay. Then came the third generation or 3G, and this was designed for voice again, but with some data consideration. So you could send multimedia and text messages, and could access the internet with 3G. Okay, and this was the first mobile broadband. Okay, and the speed was 2000 kilobits per second, or approximately that. Okay, and then came 4G, which was designed primarily for data. Okay, so this was a paradigm shift. Okay, from 3G to 4G, and everything was IP based, so the internet protocol. Okay, so the 4G entirely was designed for data communication and internet, and this was the true mobile broadband. And as we will see, the voice on 4G was basically using a technology called voice over LTE. Okay, or VoLTE in short. So the voice was also digitized in 4G, and it was packet based. Okay, so your voice, analog voice, was digitized, and then it was sent as packet switching over the 4G IP network. Okay, so we will see more on that, but this was a real paradigm shift from 3G to 4G, and of course the speed was several thousand kilobits per second. Okay, so moving on, so what 4G actually provided was high speed and universally accessible wireless service. Okay, and this was a revolution. Okay, because networking at all locations were possible between different mobile devices. So it could be your smartphones, it could be your tablets, it could be your laptops, any wireless device with a connectivity. So this was similar to the revolution caused by Wi-Fi. And we will study LTE and LTE advanced. So they are different, but again, one is the advanced version of the other. So we will study the goals and requirements, the complete system architecture, the core network, which is part of the evolved packet system, and then the LTE channel and physical layer. So this LTE actually had different releases. So basically this LTE, it was a part of the 3GPP. Okay, so if you go and search the internet, what is 3GPP? So this was the standard which started during 3G. Okay, and then different releases under these. Okay, so let's say release 1, release 2, etc. let's say. So different releases under this actually denoted different enhancement in technologies. Okay, so the LTE or the 4G, the first 4G specifications were actually mentioned in release 8, and then there were enhancements. So first we will study release 8 and then the enhancements from releases 9 to 12, and even 5G is also a part of this 3GPP releases. Okay, so 5G is basically release 16 or higher, I guess. Okay, you can look up. I'm not 100% sure, but I think it's either 15 or 16 and higher. So as you can see, the different releases of 3GPP standards actually define new technologies, and 4G is from release 8 onwards, 5G is actually 15 or 16 onwards. Okay, so the purpose, motivation and approach to 4G was basically to provide ultra mobile broadband access. Okay, so and also for a variety of mobile devices, not just the smartphone, but a tablet, a laptop, or any other handheld device with a connectivity. Okay, so the International Telecom Union (ITU) had some directives for 4G, and the first one was this all IP packet switch network. So as you saw in the first introductory slide here, so this was designed primarily for data, and it's basically an IP based protocol. So as you can see, it was initially envisaged as an all IP packet switch network. Okay, with peak data rates of up to 100 megabits per second for high mobility and up to 1 gigabit per second for low mobility applications. Okay, and then there should be some dynamicity, so the dynamically sharing and use of network resources would be possible. So these are all the directives for 4G. Okay, so this one is the all IP packet switch network. This is one directive, the peak data rates of these values. Then the dynamicity, Then the smooth handovers across heterogeneous networks, including 2G and 3G networks. Okay, so whenever a new technology comes up, so the other legacy technologies like 2G, 3G, you cannot completely rule over the other legacy technologies. Okay, so sometimes these technologies coexist. Okay, so that's why this smooth handovers across heterogeneous networks. Okay, so heterogeneous means a combination of different things. Okay, so you can see that you have 2G, 3G, everything together, and then these small cells, these are concepts related to 4G onwards. So small cells such as picocells, femtocells, and relays, so they all coexist, and also the WLANs. Okay, so all these things can support smooth handovers, okay, across the devices of all these different technologies. Okay, and then high quality of service for multimedia applications. So when you are watching a video, you would probably not want the video to stop, or you would not want to have jitters, etc. So that is meant that is what is meant by high quality of service. And multimedia applications are basically the video type of applications, or let's say the online gaming and all this high bandwidth multimedia applications. You should have high quality of service. So all these are the different directives of the 4G that was envisaged by the International Telecom Union, or ITU. And there would be no support for circuit switch voice. Okay, so this is very interesting. So this was also part of the 4G directive. So usually in 1G, 2G, etc., the voice was circuit switched. Okay, so instead of circuit switch voice, your 4G will provide voice over LTE. So the entire 4G network will be a data network, okay, supporting packets. Okay, and the voice will be also converted to digital packets, and then that will be sent through this data network. So that is called voice over LTE. And also in 3G you saw that you were using spread spectrum or CDMA type of systems. Here you will use OFDM. Okay, so in your digital communication class, those of you who are taking my digital communication class, they will study OFDM separately there. So those of you in my wireless communication class and are not attending my digital communication, they can watch my OFDM videos. So ask your friends to share those videos with you, so that you can learn more about OFDM. Okay, so this 4G and onwards, they would use OFDM instead of spread spectrum. So this table summarizes all these wireless network generations. So as you can see, the striking difference is that in 4G you will have an IP backbone instead of having the public switch telephone networks. So in fact, in 3G itself there would be the evolution of packet networks. Okay, and in 4G the network is completely IP based. Okay, and then you have OFDMA and single carrier FDMA for 4G, as opposed to FDMA and TDMA and CDMA technologies in 1 to 3G. So this is the summary of all the generations of wireless mobile communications. So moving on, when 4G was still in its early days, there were two candidates for 4G. Okay, so the IEEE 802.16 standard, which was also known as WiMAX, So this was an enhancement of previous fixed wireless standards for mobility. And then the LTE, or the long-term evolution, that we are studying. So this was part of the 3GPP, as I mentioned in a couple of slides back. So this is third generation partnership project, and this is a consortium of Asian, European and North American telecom standards organizations. Okay, so both are similar in use of OFDM and OFDMA, so both this WiMAX and LTE. But LTE has become the universal standard for 4G, and WiMAX is actually dead now. Okay, so this is interesting. If you want to know more why, then I would suggest you to do some self study, look up in the internet and find out why WiMAX didn't get as popular as LTE, and it's almost dead now. Okay, so so let's look into this LTE architecture. So some features started in the 3G era for 3GPP, as I was saying. So initial LTE data rates were similar to 3G, and then in the 3GPP release 8, okay, there was a clean slate approach. Okay, so there was a completely new air interface based on OFDM, OFDMA and MIMO. Okay, and then 3GPP release 10 was known as LTE Advanced. So there were more enhancements in this release 10, and further enhancements were there in releases 11 and 12. Okay, so so this is the comparison of the performance requirements for LTE and LTE Advanced. So let's look into them. So first thing is the peak data rate. So we have different data rates for downlink and uplink, of course. So you are actually downloading more data and uploading less, so obviously the downlink data rate has to be higher. So this is 100 megabits per second at 20 megahertz. Okay, so 20 megahertz is the frequency, I mean spectrum range or central frequency of the spectrum, and 100 megabits per second is the downlink speed. Okay, so this is for LTE, and for LTE Advanced you can see that already you operate in a higher spectrum range, and also the data rate is higher, 1 gigabits per second. For the uplink you have less data rate, so 50 megabits per second for LTE in the same spectrum range, but for LTE Advanced it is 500 megabits per second. The control plane delay, so this is again interesting. So control plane delay means the control plane refers to the network management plane. Okay, so let's say you have your network. Let's say this is your network. Okay, so here you have different nodes and then links. Okay, like this. So let's say this is your network, and then on top of this there is something called control plane. So this contains some devices like some large computers, okay, or data centers that will manage and control this network. Okay, so in the cognitive network class you learned something about software defined networking or software defined radio. So basically there is a software residing here, okay, in different large supercomputers that are constantly monitoring these network devices or nodes and exchanging data with them, and based on that they are asking this device to perform certain tasks, let's say routing or finding a path through the network, etc. So basic concept is that this control plane actually is a set of devices or supercomputers that are controlling the network, as the name suggests. Okay, So in case of your LTE, the control plane delay when the devices are idle to connect it is less than 100 millisecond, and when the devices are active it should be less than 50 milliseconds. So what that means is that the total round trip time between this control information exchange from these network nodes to the control plane has to be less than these value for idle to connected state, and for dormant to active state it has to be less than 50 milliseconds. And these values are even less for LTE advanced. So this is less than 50 milliseconds and less than 10 milliseconds. For 5G actually these values are of the order of 1 millisecond, 1 to 10 milliseconds. Okay, so 5G has even more strict requirements on this control plane delay. For the user plane, okay, the delay is even less, okay, less than 5 milliseconds, and this is lower than LTE for LTE advanced. Okay, and spectral efficiency, again these are different for downlink and uplink. So this is actually 5 bits per second per hertz. Okay, so this comes directly from these values. If you divide 100 megabits per second with 20 megahertz, so this is the spectrum, so per hertz you will you will transmit 5 bits per second. Okay, and this is 2.5 bits per second per hertz, and these are the MIMO actually that you are using. Okay, so 2x2 MIMO or 1x2 MIMO. So for downlink you are using 2x2 MIMO, for uplink you are using 1x2, and then for LTE advanced you see you are using higher number of antennas, so you are using an 8x8 MIMO for LTE advanced downlink and a 4x4 MIMO for LTE advanced uplink. And the mobility is up to 350 km per hour for LTE and up to 350 to 500 km per hour for LTE advanced. So basically what does this mean is that if you are traveling in a high speed train, you can smoothly browse the internet from your smartphones if you are using LTE or LTE advanced. Okay, and that was indeed the case. Okay, so couple of years back I was when I was in China, I was traveling from Beijing to Guangzhou for a conference on a high speed train, and the speed was incredibly high, 341 kilometers per hour, and I could browse the internet on my phone, and I could take a snapshot like this and share it with my friends from the train itself. So that was incredible, and that indeed is the promise that LTE is making. Okay, so moving on with the LTE concepts in detail. So let's talk about the LTE architecture in more detail now. So the LTE architecture has something called the evolved node B or E node B. Okay, so this E node B is a very important part of the LTE architecture. This is basically equivalent to the base station. Okay, to the base stations that you have actually. So this is the technical name of the LTE base station, which is called E node B or evolved node B. Okay, so most devices connect into the network through this E node B. Okay, which is obvious. So there was a node B in the previous 3GPP release. Okay, so this was an evolution of that. So as you have seen in the previous slides, so there was a jump in LTE release 8, which was a clean slate approach, and OFDMA came instead of CDMA. So this E node B is based on OFDMA, instead of this just the node B, which was a part of the previous release where CDMA was used. And not only that, on top of that, this E node B has its own control functionality, okay, rather than using the radio network controller. Okay, so the E node B supports the radio resource control, admission control, and mobility management by itself. So it has its own control functionality. Okay, this was originally the responsibility of the radio network controller in the previous releases. Okay, so E node B is a very important part of the LTE architecture. So here in this diagram you can see you have these E node Bs, which are basically the base stations. So as you can see, your mobile or the user equipment UE is connecting to the E node Bs through this through the air interface, and then they are getting connected to the rest of the internet. So there are other entities in the LTE architecture, for example the MME, the SGW, the PGW, HSS, etc. So we will discuss them in detail. So let's go through them. So this diagram is the entire architecture of the LTE network, and I just showed you to highlight what is an E node B here. We will also discuss all these different entities of the network very shortly. So let me go through the rest of the slides and then we will get there eventually. So you saw that there is an E node B. Now the entire architecture of the LTE system is called the evolved packet system. Okay, so this entire thing, okay, this entire thing is called the EPS or the evolved packet system. Okay, and usually, so the 3GPP standard, so LTE is a part of this 3GPP standards. Okay, this is LTE is release 8, right? So generally speaking, these 3GPP standards, they have these two parts of the network. Okay, one is the radio access network and the other is the core network, and each of them evolve independently in different releases. Okay, so in case of the LTE, okay, the RAN is called the evolved UMTS terrestrial radio access, okay, or in short EUTRA. Okay, so this is the enhancement of the 3GPP's 3G RAN, and this is called the evolved UMTS terrestrial radio access network. Okay, so this part as you see, this top part, okay, this is the LTE EUTRAN. Okay, so this is the radio access network part. Okay, and the rest remaining is the core network, whatever lies below. Okay, this solid line. Okay, this is the core network. Okay, so we are now focusing on the RAN part. Okay, so the RAN is called EUTRAN in case of your LTE. Okay, so any 3GPP standard would have a RAN and a core network. LTE also has those. In case of LTE, this RAN is called EUTRAN, and the E node B is the only logical node in the EUTRAN. Okay, there is no radio network controller, because the radio network controller now is part of the E node B. Okay, as you saw in this slide. Okay, so there is no RNC. E node B supports all these functionalities of the RNC, and therefore for your EUTRAN, this E node B is the only logical element. There is no other elements here. Okay, you can see there are many elements, 1, 2, 3 and 4 in the core network, but in the RAN part of the LTE, which is called EUTRAN, The E node B is the only logical element. There can be many E node Bs, but the type is only one. Okay. So that is the RAN part here. Okay. So basically EPS has EUTRAN, and then the core network, which in case of your LTE is called EPC or Evolved Packet Core. We will get into the details of this later, but right now in this slide what you just learned is EUTRAN, which is part of the EPS. Okay. So now we come to the core part, okay, the EPC. Okay. So now that we are done with this part, now let's focus on the EPC. Okay. So this is the EPC, which is called the Evolved Packet Core, or this is the operator or the carrier core network. Okay. So this means whichever is the owner of the LTE network, whichever service provider or operator, let's say China Mobile is an example of an operator, okay, or China Unicom, whoever is owning the network, that they have this core network. Okay. And it is important to understand the EPC to know the full functionality of this architecture. Okay. So if you go back few slides, so this is the EPC. Okay, this part. Okay, and this was the EUTRAN, and this is the EPC or Evolved Packet Core, and then together they form the Evolved Packet System. Okay, so we will discuss the details of these entities within the EPC, but let me go through what I have first. Okay, so this is so some of the design principles of the EPS are these. So of course it's a clean slate design. It doesn't match with what we have before, so everything is getting designed and everything is new from a clean slate perspective. So packet switch transport for traffic belonging to all QoS classes, including the voice or the conversational traffic, then streaming data, real-time data, non-real-time data, and background data. Okay. Then the radio resource management for the following, for example, end-to-end QoS, transport for higher layers, load sharing, balancing, policy management and enforcement across different radio access technologies. All these things has to be maintained. Okay, so resource management is another principle of the Evolved Packet System. Then integration with existing 3GPP standards, so 2G and 3G. Okay, this is also important, as I was saying. Even though the LTE design is a clean slate approach, you cannot totally ignore the other existing legacy technologies. So they coexist together. So you have to have some integration with these existing technologies. Then the next design principle is a scalable bandwidth from 1.4 megahertz to 20 megahertz. Okay, and then carrier aggregation for overall bandwidth up to 100 megahertz. Okay, so we will study what is carrier aggregation later on, either in this lecture or in the next one. So we will discuss at that time more of carrier aggregation. So these are the different design principles of the EPS. Okay, so now let's see what are the functions of the EPS. Okay, so obviously we should have network access control, including network selection, authentication, authorization, admission control, policy and charging enforcement, and lawful interception. Then the next function is the packet routing and transfer. So we have an entirely IP based packet network, so the packet routing and transfer is important. Then security, including ciphering, integrity protection, and network interface physical link protection is also a function of the EPS. Mobility management, to keep track of the current locations of the UE. Then radio resource management to assign, reassign and release radio resources. Then network management to support the operation and maintenance of the network. And then the several IP networking functions, connections of the node Bs, EU-TRAN sharing, emergency session support, etc. So all these are the different functions of the EPS. So let's look into more details of the evolved packet core. So traditionally circuit switch, but now entirely it is packet switched. Okay. So in the 4G LTE, as you have already seen in this lecture or in this video session, this is purely based on IP and entirely packet switched. So the voice is supported using VoIP or voice over IP, and initially the core network was called the System Architecture Evolution or SAE, okay, but now it is called EPC. And I have already shown you this diagram, and we have discussed mostly the LTE radio access network, so which is this part, which is also called EU-TRAN. So now let us focus more on these components of the EPC. Okay, so the first component is called MME or Mobility Management Entity. Okay, so the Mobility Management Entity supports user equipment context, identity authentication and authorization. Okay, so this is your MME. Next is the Serving Gateway or SGW. So the Serving Gateway receives and sends packets between the eNode B and the core network. Okay, so here you are eNode B, which are the logical parts of the EU-TRAN. They are sending the packets and to this SGW. So this is the gateway or serving gateway to receive the packets from the LTE radio access network, or more specifically from the eNode Bs, and then it connects to the core network. Okay. Then comes the Packet Data Network Gateway or PGW. So this connects the EPC with the external network. So as you can see, your PGW connects the network, the LTE network, with the rest of the internet or the external networks. Okay. And then comes the Home Subscriber Server or HSS. So this is basically a database of user related and subscriber related information. So all the subscriber data is stored in this HSS. And then there are several interfaces. So first one is the S1 interface between the EU-TRAN and the EPC. So this is the S1 interface. Okay, so this is the S1 interface, and this has again two parts. Okay, this is used both for control purposes and user plane data traffic. Okay, so as you can see, there are different lines. The solid line indicates data traffic. So the eNode Bs are exchanging data traffic through this S1 interface to the SGW, and then the MMEs are also exchanging control information, which are denoted by these dotted lines. So the control traffic stands for the dotted line. So they are exchanging, the eNode Bs are exchanging control information to the MMEs through this S1 interface as well. And depending on whether it's a data or user traffic or a control traffic, the S1 interfaces are named differently. So this one is S1U and this one is S1 MME. So these interfaces are called S1 MME, and the user traffic interfaces are called S1U. Okay, so this total thing is called the S1 interface. Then the X2 interface for eNode Bs to interact with each other. So different eNode Bs are interacting with each other using this X2 interface. Okay. and again these are for both control purposes and for the user data traffic purposes. Okay, so these are the different components of the EPC. Okay, so let's now look into the functions of the MME. So the main functions supported by the MME can be classified into these two categories. So the functions related to bearer management and the functions related to connection management. Okay, so I will explain what is a bearer later. We will come to that shortly in this lecture. So the functions related to bearer management, this includes the establishment, maintenance and release of the bearers, and is handled by the session management layer in the NAS protocol. Okay, so we will also explain what is NAS protocol when we go through the LTE protocol structure. Okay, the other function of the MME is the functions related to connection management, and this includes the establishment of connection and security between the network and the UE, and is handled by the connection or mobility management layer in the NAS protocol layer again. Okay, so NAS actually stands for non-access stratum. Okay, so we will go through this separately in a future slide very shortly. So so these are the two functions of the MME. So as you see, so NAS, you just saw that these were the part of the NAS protocol layer. So NAS stands for non-access stratum protocols, and so there are two actually types of protocols. One is the access stratum protocol and the other one is the non-access stratum protocol. Okay, so for interaction between the EPC and the UE, you are using these non-access stratum protocols. Okay, and these are not part of the access stratum that carries data. Okay, so the access stratum, so basically now that we have gone through this bullets, so we can conclude that access stratum is basically related to data, and non-access stratum or NAS is basically related to control and management. Okay, so these are the two different sets of protocol in LTE, by the way. So access stratum and non-access stratum. Now we are focusing on non-access stratum. So these are for interaction between the EPC and the UE, and not part of the access stratum that carries data. These non-access stratum protocols are also involved in the EPS mobility management and also the EPS sessions management. Okay, so these are the different functions of the non-access stratum protocols, and the functions of MME are also part of the NAS protocol layer. Okay, so now let's move on with the LTE resource management. So as I was mentioning couple of slides back, the term bearers, and I also said that I will explain it very shortly. So now that we are discussing LTE resource management, we come into the concept of bearers. So LTE basically uses bearers for quality of service control instead of circuits. Okay, so this is similar, basically the bearers are similar to the virtual circuit method of packet switching. So LTE is purely packet based network, and we are using packet switching, and these bearers are basically similar to the virtual circuits. So you establish an end-to-end virtual circuit and then you send your packets through that virtual circuit. The bearers have the same role in LTE. So in fact the virtual circuits in LTE are called bearers. Okay, So you have EPS bearers, okay, between the PGW and the user equipment. So a complete end-to-end path, as you can see from your user equipment, is actually going. So if you want to establish a internet connection from your UV to the internet, a complete end-to-end path would be from the UV or the user equipment to the PGW, okay, and then towards the internet, but we are interested only up to this PGW because we are looking into the LTE architecture. So for LTE, EPS bearer actually can be established from UV to PGW, and that's what is mentioned here. So the EPS bearers are between PGW and the UV, and they map to specific QoS parameters such as data rate, delay, and packet error rate, okay. So so the LTE, they use these bearers, and there are different bearers, okay. So depending on the quality of service that it is supporting, okay. So basically the quality of service parameters, according to these parameters you define service data flows, okay. So these service data flows, they differentiate the traffic flowing between applications on a client and a service, okay. So these SDFs can be categorized based on these QoS parameters, and then these SDFs are mapped onto the different EPS bearers for QoS treatment, okay. So basically these SDFs or service data flows, you have a goal for each of these SDFs. So let's say if it is a video based service, okay, then the SDF will say that this would have very low jitter, let's say, very high bandwidth, etc. So these are all different QoS parameters, okay, high data rate, etc. So this SDF or service data flow will define the QoS parameters based on the service, which is video. The service can be just voice, okay. So the voice can be part of another SDF which may not require this low jitter, because for voice you may not need low jitter, but and also you may need a moderate bandwidth instead of a high bandwidth. So all these things will be defined under these SDFs, okay. So now this SDFs being defined, you have to map these SDFs on different EPS bearers, okay. So these bearers are basically, let's say, whether, so depending on the time you need, let's say you are traveling, okay, from Beijing to Shanghai, let's say, okay, and before traveling, if you need to find out whether you want to travel, you know, in a less time, okay, or you can afford more time, but you want to travel with a less cost, let's say. So based on this, you can either take the road, you can travel by a car, or you can take the airline, or you can take, you know, the high speed train. So these road or high speed train or airline, these are the bearers, okay, and these SDFs are your requirement to travel either faster or not so faster, at a high cost or a low cost, etc. So these SDFs allow traffic types to be given different treatment, and these treatments are associated with the different bearers, okay. And the end-to-end service is not completely controlled by LTE. So the LTE only controls between PGW and UV. For the remainder of the path, from PGW to the rest of the internet, the LTE cannot control the service. So that's what is meant by this bullet. So here is a picture that will summarize what I was explaining so far. So as you can see, you have the user equipment, and then this is another peer entity, okay, that is part of the internet. Let's say this is a router, okay, that is there in the internet. Okay, so you have to establish a connection between your UE and the peer entity in the internet, and then the rest of the connection will be taken care of by the different routers in the internet. Okay, so here these are the different parts of the LTE. So E node B, serving gateway, packet data network gateway or PGW, etc. And then these two are part of the EPC, and this is the part of EU-TRAN. And then you define an end-to-end service from this UE to the peer entity, and then you map this service into different bearers. Okay, so this end-to-end service will be part of different SDFs with different QoS. So different SDFs with different QoS requirements, and then they are mapped to this different bearers. So you can have an EPS bearer and an external bearer. So from packet data network gateway to the rest of the internet, you have an external bearer, and these from PDN to the UE, these are all part of the LTE network. So here you can have EPS bearer, and these are basically the virtual circuits actually. So then this EPS bearer can be again subdivided into radio bearer, S1 bearer, and S5/S8 bearer, okay, depending on these interfaces. So this is the radio interface, so this is therefore called the radio bearer. This is the S1 interface, which you learned just a few minutes back. So this is the interface between the EU-TRAN and the EPC. So this bearer is called S1 bearer, and then from SGW to PGW the interface is called S5/S8. so you have a S5/S8 bearer here. Okay, so this is all about the LTE QoS bearers. Okay, so then there are several classes of bearers, as I was saying. So if you go back to the analogy of, you know, whether you would use the road or airline or high-speed train, depending on your requirements. So those are equivalent to this different classes of the bearers. So you can have guaranteed bitrate bearers. So they guarantee a minimum bitrate and possibly higher bit rates if system resources are available. So let's imagine that this is the road network, okay, which provides basically a minimum bit rate. Okay, this is useful for low QoS services like voice, okay, interactive video or real-time gaming. Actually voice is low QoS, but these are not, but you can still use a guaranteed bit rate with these services also. It all depends on your requirements. And then you have non-guaranteed bitrate bearers. So they does not guarantee a minimum bitrate. Oh, sorry, this guaranteed bitrate is basically, let's say, this cannot be the road. This is the road, okay. So because there is nothing guaranteed here, okay. So this is basically, let's say, the equivalent to the high-speed rail, let's say, or even the airline, because they guarantee a bit rate, and then you can always get more than that, or at least that much, okay. And that's why This is useful for voice, interactive video, or real-time gaming. Okay. My apologies for confusing you. So this is guaranteed bitrate, and this is equivalent to the road network, where you don't have any guarantee. Okay, you're not guaranteed a minimum bitrate, and performance is more dependent on the number of UEs served by the E node B and the system load. So as you travel driving a car through a road, the performance is dependent, or the speed is actually dependent based on how much traffic congestion you have in the road, okay, and how, let's say, others are driving. If they are driving slowly, then you have to also drive slow, etc. And this is useful for actually low QoS services, so email, file transfer, web browsing, and peer-to-peer file sharing. Okay, so so you have GBR and non-GBR bearers for the different classes of bearer, and then each bearer is given a QoS class identifier, or QCI, and this table actually summarizes the different QCIs. So you have 9 QCIs actually. 1 to 4 is guaranteed bitrate, and 5 to 9 is non-guaranteed bitrate, and usually the value 9 is the default. Okay, and you can set this QCIs, you can program and set this QCIs, or sometimes depending on the network's requirement, automatically this QCIs can change, but this is the default. Okay, and then under each QCI you can see, or rather under each resource type, where GBR or non-GBR, you can see that there are different priorities. Okay, so you can set the priority levels, okay, based on these numbers. Okay, so so if you have or in other words, within the GBR, so GBR has 1 to 4. Okay, sorry, guaranteed bitrate is 1 to 4. Okay, and within this guaranteed bitrate, the priority is in this order. So the QCI class 2 has the highest priority, followed by 4, then 3, and then 5, and then 1. Okay, and then 6, and then 7, and then 8, and then 9. Okay, and then the packet delay budget is defined based on these priority values, and the packet error loss rate is also different based on these priority values. And the example services of these different QCIs are given here. So you have conversational voice, conversational video, real-time gaming, non-conversational video, etc. Okay, and then here you also have different service types for the non-GBR cases as well. Okay, so so let's move on and look into the more details of bearer management. So each QCI is given a standard forwarding treatments. So the scheduling policy, the admission thresholds, the rate shaping policy, the queue management thresholds, the link layer protocol configuration, these are all, you know, these will all change based on the QCI class. And also for each bearer, the following information is associated. So the QCI class identifier value, and the allocation and retention priority, okay, or ARP. So this is used to decide if a bearer request should be accepted or rejected. So you saw in the previous slide that there were these priority values as well. And additionally, for guaranteed bitrate bearers, you have the guaranteed bitrate, or the minimum rate expected from the network. You also have the maximum bitrate, which is the bitrate not to be exceeded from the UE into the bearer. Okay. So the different functions of the EPC, or the evolved packet core, are as follows. So you have mobility management, you have under mobility management, you have this X2 interface which is used when moving within a RAN coordinated under the same MME. Okay, so you have this X2 interface between these different node Bs, and this interface is used when moving within a RAN coordinated under the same MME. Okay, so if you go back to the structure here, so under the same MME, okay, if you can see within this MME both these E node Bs are there, and if your U is moving from the range of this E node B to this, then the X2 interface, which is between the E node Bs, they actually coordinate this mobility between the two MMEs. Okay, so that's what is said here. X2 interface is used when moving within a RAN coordinated under the same MME. The S1 interface is used to move to another MME. Okay, and hard handovers are used. So unlike CDMA, where soft handovers were there, here in 4G LTE hard handovers are used, where UE is connected to only one node B at a time. Okay, and then there are other functions of the evolved packet course. For example, the inter-cell interference coordination. So this reduces the interference when the same frequency is used in a neighboring cell. The goal is an universal frequency reuse. So therefore, one must avoid interference when UEs are near each other, and the interference randomization, interference cancellation, coordination and avoidance techniques are used. Okay, so the later releases of LTE have improved this interference control. Okay, as compared to later release 8. So the LTE channel structure and protocols, we will now focus on these. And LTE has a hierarchical channel structure, and also it has several layers in its protocol stack. So as common for any networking technology, you have a layered protocol structure, and an LTE radio interface is divided into control plane and user plane, and the layers of the protocols vary based on whether it's a control plane protocol or user plane protocol. So the user plane protocols are part of the access stratum protocols, as we discussed briefly previously, and the control plane protocols are called non-access stratum. Okay, so the user plane protocols transport packets between the UE and the PGW. So UE is the source and PGW is the ultimate destination within a LTE network, and PDCP transports packets between UE and eNode B on the radio interface. Okay, so this is one of the protocol. There are other protocols also. So this is the radio LTE radio interface protocols. So we have the control plane and the user plane. In the control plane, you have this radio resource control layer, and which you don't have in the user plane, but the rest of the layers are both shared by the control plane and the user plane. So you have PDCP, RLC, the MAC layer and the physical layer. Okay, so we will study in details all these layers. So first comes the radio resource control. So this performs control plane functions, as you saw here. So this is only part of the control plane, RRC, or radio resource control. And through RRC idle and RRC connected connection states. So RRC has two connection states. Then comes the PDCP, or the packet data convergence protocol. So this delivers packets from UE to the eNode B, and this involves everything: header compression, ciphering, integrity protection, in sequence delivery of the packets, buffering and forwarding, everything. Okay, so that's the PDCP. Then comes the radio link control. Okay, so this segments or concatenates the data units. and also performs the ARQ when MAC layer HARQ fails. And the MAC layer performs the HARQ or hybrid ARQ. You have studied this before, so this is coming into practice here. And the MAC layer also prioritizes and decides which UEs and radio bearers will send or receive data on which shared physical resources. So this is a typical MAC layer function, medium access control. Okay, so how will the shared medium be accessed by the different UEs? That is also done here in the LTE MAC layer. And it also decides the transmission format, that is the modulation format, code rate, the MIMO rank, and the power level. And finally the physical layer that actually transmits the data or the bits. Okay, so this is the LTE protocol stack from the user plane perspective. Okay, so these blue parts are the user plane protocol. Okay, and the greens are the control plane protocols. So between the UE and the E node B and the SGW and the PGW, you have these different protocol layers. Okay, so the layer 1 is there in all the devices, as you can see. So this is the physical layer. Then the MAC layer is between the E node B and the UE. Okay, and then the E node B has a separate set of green protocols, which are the control protocols for the E node B, and they have connections to the SGW. So this SGW is entirely for the control purpose. So all the layers here are green, and then the PGW is also mostly associated with the control functionalities. So so this is the user plane protocol stack, and these are the control plane protocol stack. Okay, so you can see that again you have this distinction, green and blue, for your protocol stack. Actually the blue is control. I'm very sorry. So in the previous slide, actually the blue is the control part. Okay, and the green is the data part. So this is the control plane stack, and this is the user plane stack. Okay, so I will stop here for this video lecture, and then we will continue more and discuss more about the LTE in the next video lecture. Okay.